So I'm Brian. I'm a professor at Brigham Young University. If you guys don't know about BYU too much, besides maybe sports and our football team that isn't very good for the last 10 years, we're one of the largest private schools in the country. We have 34,000 students, and in my department, we teach 12,000 students every year. So, so we're pretty big, and I'm the developer of the Labz. So we started working on these labs in 1998 when I was a first-year faculty member at BYU, and they've gone through lots of different versions and iterations since then, and you're seeing the most recent ones. So shall we get started, Heather?
Sure. I just wanted to chime in and say, feel free to ask questions in the comments. That's probably the easiest way to moderate these. You're welcome to turn off your camera if you want to. We don't care. We will blur out your video feed when we post these webinars online, so don't worry about that. We also, I will interrupt Brian whenever you've got questions that I can't answer by text, or if you want, you can raise your hand and we can unmute you, or you can unmute yourself to chime in directly, as long as it's not too crazy here.
Yeah, so welcome everybody for coming. So we do these every Tuesday and Friday for the foreseeable future. And so, you know, if you have other colleagues who've missed this and they want to have them watch it, you know, we'll do another one on Tuesday, and we'll post our link to these webinars up on our website. So, like I said, I'm the developer of these labs, and we've been using them for a long time. They were all developed at BYU, and we licensed them for many years, for like more than 15 years, to Pearson Education. And so they were quite heavily used back in the day when we had CD-ROMs and distributed them as a CD-ROM package. So a couple of years ago, we took the licenses back from Pearson, and we started Beyond Labs last year. It's been about a year now that we've been officially in business, and we have a small team. Most of us have other jobs that we're doing, and so we've kind of taken the labs and repackaged them and updated them a little bit, and we're taking all of our revenues right now and funneling it all the way back into further development of the labs, which maybe at the end I can show you where we're going with those over the next couple of years. So yeah, like Heather said, feel free to ask questions. This is super informal, and I'm just here to make you feel comfortable with the labs and show you how maybe some suggestions of how we use them. So I'm going to share my screen here, and with that, I'm going to minimize all of the pictures down here so I can have the screen. So what I'm going to do is kind of go through a couple of different descriptions. So I'm going to go through and kind of show you the client and how it works. So here's the client that you see on the screen right now. Kind of go through and tell you how it's used, and talk about a couple of common issues that students run across in using it, and just give you a broad 30,000-foot view of how to take advantage of the client and its worksheets. And then I'll go into and do some demonstrations in chemistry and organic chemistry. And I haven't heard about anybody for physics, so I'll probably ignore that and maybe do a couple of demonstrations in biology in our molecular biology lab that we have there.
Oh, we just got a physics one, Brian. We do have to hit physics. That's good.
All right. So, you know, even though these labs and these lab benches are packaged up into these different products for chemistry, you know, you don't have to limit yourself to say, hey, I'm a chemist, I'm just going to use the chemistry ones. Feel free to mix and match. So for example, physics has a density lab that we're discovering a lot of chemistry faculty are using as well. So feel free to have them install all of the lab packages that you might need and use all the worksheets, whether they're higher ed or high school worksheets. Um, so the client, so we kind of patterned this after Adobe's cloud client, in the sense that Adobe had these massive packages like Photoshop and Illustrator and Dreamweaver, et cetera, that were installed locally, and they needed a way to manage those and to manage the licenses. So what we did is we created this client last year that houses the content and the labs and the licensing for you and your students. So this tab includes all of our 5 different products. I want you to point out that this says higher ed or high school. I'll show you how that works. The labs don't change. What changes is the content we use in the labs. So when you first install, this won't say open, it'll say download. You click on it to download, it'll download and install locally for Windows and Macintosh on your computer, and then you just click to launch it. So this is kind of where the access point for the lab. So it's kind of like, I'm gonna go open my door and go into the labs, this is where you would go. We have content that we've developed over the years for these labs. They're high school level, higher ed, and for physical science, it's more middle school, but there's no reason why you can't use it. It's all good content. What changes is the level and the assessments questions that we're gonna ask. So the labs don't change. They're just rooms, they're benches, they're simulations. What changes is the pedagogy and the structure and the levels that we're going to be teaching students. So we divide all of these lab activities, we call them worksheets, if you will, into these different subjects. So here's chemistry, and then we divide it up into a high school version and a higher ed version. So if you go to the higher ed version, then we further divide this up into topics. And so here's atomic theory, and then now you get to this list of lab activities that we have for Thomson or Millikan or Rutherford, photoelectric effect, and so on. So these are PDF files. So if I were to do Rutherford, I'd click on Rutherford. It opens up with the default reader for PDF files. And here's a PDF lab activity having students actually do the Rutherford experiment. So we have background information, and these are structured. We give them step-by-step instructions with assessments for students. So in a sense, this is a drop-in for you, that if you just say, hey students, here's your license code, or go purchase a license code, install the labs, go do this experiment. Most of the onboarding is put onto the student. Obviously you need to go through and decide which ones you want to do, but these are pretty, we've written about 80 worksheets for higher chemistry, higher ed. We have like 40, I think, for physics. We have 120 for organic chemistry. We have 30 here for high school. High school is really no different. They're organized here by NGSS standards, but these are just other worksheets that you could use. And so yeah, it says Rutherford's, but the experiment might be a little different, or the questions might be more simple. So it's just a level issue. And so this is kind of how we structure to use the labs. Imagine that you have a real lab, you have a door, students go in, they have lab benches, they have drawers, they have a stock room, cabinets that they can get equipment, and the room doesn't do anything. You as the teacher, as the instructor, have to define the learning objectives, the learning goals, provide the procedures, the instructions, the background, to make it a learning environment for your students. So the virtual labs take that exact same mentality. We just provide a room that's open-ended, that where you can do almost anything you want inside of that room, and then these worksheets are a way to get there. So labs,
optional.
worksheets.
Many people use our labs without using our worksheets. They write their own content, write their own directions,
Yep.
whatever you want for your own students. The worksheets are completely on the side.
Yeah, so yeah, they're not integrated inside, except how in a way that I'll show you in a minute. But you're certainly welcome to modify our worksheets. We can give you Word files of these worksheets that you can then modify to fit your curriculum, or change, hey, I don't want to use hydrochloric acid, I'd rather go use nitric acid or whatever, you know, you can go do that. And so it's completely open to you, and it's really a nearly unlimited possibilities of how you can use the labs. This is the license tab. So either students purchase these license codes on their own through our website, and then they enter that code here, submit it, and it's good for a year, or we will give you a single code good for X number of uses. You hand that code out to your students, they enter the same code, we track that, submit the activation code, and then same thing. So this is what activates it. When you install this for the first time, it's good for 2 days for free, and then after that it shuts down and you have to use a code. The settings here this is where you can control for example here, the high school, the level. It doesn't change the lab, it only changes how we hook in the worksheets. So I'll show you that in a minute. So you saw that we had high school worksheets, higher ed worksheets. This is where you change that level, and it changes the level right here, and you'll see how that works in a second. So that's the client, that's how it kind of works, and how things are wrapped around it, and we control things. So when you purchase this, you get access to all the labs. You just choose which ones you want to use. So any questions before I go into general chemistry?
I was just going to chime in. For many people, that they're finding that useful because you get a 1-year license. So if your student's taking OChem over the summer and then they're taking physics next fall, they can use the same program. So across universities, it can be really useful.
And like if you're taking a 2-semester sequence in chemistry, in general chemistry, use it for both semesters. So, all right, let's go into kind of show you a lab. So I'll start with general chemistry and show you how that works. So, so I just clicked on it, and this is our landing page. So each one of these icons represents a lab bench, and I'll show you a bench in a minute. We also have an electronic lab book that they can open here. I'll show you how to use that in a minute. We have help files that nobody ever reads, but there's a lot of detail there on how to use the labs. Down here in this corner is a worksheet table of contents. So I showed you the chemistry. So right here, I showed you here in worksheets and chemistry and higher ed, you'll notice that this topic sequence is the same thing as over here. So if you want to tell them to go do one of our worksheets, what they would do is say, hey, you need to go to atomic theory. And what they would do is then click on the Rutherford, if that's the one you assign, and then you would click on that. And so what that does is that brings them right to the right lab, and we have the ability to preset the lab into a certain configuration that's going to match up with the learning activities. So for example, let's say that you were teaching titrations for acid base. You may want them to focus on how to build a titration experiment. So how to weigh it out, how to do the burette, how to choose the right indicator, and so on. Or you may want them to say, not focus on actually building the experiment. You may want them to focus on what a titration looks like. You know, how does the pH change as a function of the titrant? And so we have the ability to control these presets that match up to these lab activities. So these presets are a big part of how the labs work. So this one, I just chose Rutherford. So I have an alpha particle source, I have gold foil, and I have a detector. I'm going to change the resolution on my monitor here so it comes up a little better, a little easier on, since I'm sharing my screen. So these are fixed graphics, so almost the worse of your resolution of your monitor, the bigger it's going to be. And so I can go over here and click on my detector, which is my phosphor screen, and show you what the Rutherford experiment would look like with the phosphor screen. So we have procedures. Students wouldn't have to figure this out. We step them through. But here's alpha particles going through gold foil, and this is what you would see. You would see a fat spot, and then you would see these alpha particles being deflected at a wide angle. This is real data. This isn't, manufactured or guessed. This is actual statistical backscattering data that we captured on our own instruments at BYU. And we did that for 65 different metals. So for example, a student can come over here and say, hey, I'm just going to move my gold off. What happens? What changes? Well, I see a little spot from my alpha particles. What happens if I shut my shutter? What happens if I turn it on? I can go in here to my stock room, and I have a collection of thin films. Obviously some of them have to be virtualized, like I'm not going to have a thin film of sodium sitting in the air, but I can go over here and click magnesium and say, hey, what happens if I go put magnesium in there? Oh, look at that. This is really different. How can I understand that? And so I'll just go back and put gold back in. But you kind of see the open-ended nature of the lab. The problem is that it is open-ended, so you need to structure it for the students. So that's what the lab activities do. So here's an example of Rutherford. We can step them through, procedures, move the detector over here. Hey, I still see alpha particles being deflected at a pretty wide angle. I can move it over here to the side, and boy, I just got one. So I'm seeing about 1 million alpha particles every second coming out of my alpha particle source, and I'm seeing it about 1 every second. So I click on a persist button, and then I start recording where these go. I can click here on a record button, and then these results get stored over here in my lab book. So I can go over here and do the same thing. I can start showing them what that same experiment is, click on my persist button. So this is a way for the student to record what they're seeing and for other people to see it and look at it. So I'm spending a lot of time on this experiment. I just wanted to show you this is kind of how it works. This is our quantum lab bench. I can click reset lab, clean it up. I can go into my stock room, and in this stock room has all of these different kinds of sources with these kinds of detectors. So we have spectrometers, video cameras, photodiodes, bolometers, oil mist, liquids and metals and gases, and 2-slit devices. And so they can mix and match and do all kinds of these different experiments. All of the labs also have a clipboard, and these clipboards have classic common experiments. So I just showed you Rutherford, but here's Millikan oil drop, for example. Already preset. I can change the voltage being applied and move my oil drops around. I can do 2-slit diffraction with photons, change my slit spacing, change my wavelengths of my light, change the power coming out of that, and then see how that changes. We use this for Heisenberg's uncertainty principle. You can do photoelectric effect with the phosphor screen, so I can, change the wavelength of my light and see if I'm kicking off electrons or not. Or I can go do a photoelectric experiment with a bolometer and then actually measure the energy of these electrons coming out as I change, or as I change the intensity of my light. And so lots of these options. Obviously, this lab focuses on atomic theory and things like that. But the gist is that stockroom, equipment, open-ended, you see how the worksheets work, things like that. So that's an overview. All the labs work this way. Lab benches, worksheets, you go into one. I showed you quantum mechanics. That's kind of how it works. Clipboards, open-endedness. Each of the labs, though, have their own personalities because they have their own set of experiments. So this is the inorganic qual. This was actually the first one that we did back in '98. This is obviously its 4th iteration. Graphics didn't look nearly so nice back then. But here I can grab an empty test tube. So you notice here I have a stock room again. I have a clipboard, I have a lab book, and I just grabbed a test tube, and I'm going to show you a real picture of what would be in that test tube, which is empty. Then I can start adding any of these cations. So I can add any of them, any combination, any order. And I'm going to show you a real picture of what the real chemistry would be. So here's copper, for example. I can throw in my cobalt, and I throw in my chromium. I show you here because they made it. They know what's in it, shows the chemical state. Now what I can do is start doing these lab manipulations. So I could go do a flame test. I'm going to show you a video of what that flame test would look like for those cations. I could do it with the cobalt filter in front. I could smell it, okay? I can do any of these manipulations, and then I have these 11 reagents that I can add any order, any combination, any sequence that you want, and I'm going to show you the real chemistry. So this is not based on solubility tables. This is based on real chemistry, real permutations. We spent 2 years, 1998 to 2000, with 4 students working about an average of 100 hours total a week to go do all the chemistry of all these cations and their interactions to show you what the results would be. So we have kinetics built into it. So for example, some of these reactions are slow, so you're not going to see them here, right? Even though thermodynamically they may be favorable. So let me show you how this scheme would work. So here we can do a scheme. I could just say, hey, I want to go do pH 4 or 7. I can go to pH 10, and now I've shown you that I formed precipitate for all of them. Notice here that this cobalt is not a cobalt hydroxide, it's a cobalt hydroxide nitrate. We actually spectroscopically identified these compounds to make sure they are what they're supposed to be. I can go to sodium hydroxide. Notice that sodium now is in my cation list. If I do a flame test now, you're going to see that you see a sodium flame that masks everything. Now that I have copper and cobalt as precipitates, chromium's in solution, I can centrifuge that, and then I can decant. And I can click here on the label to label this test tube. Here's chromium. Now I'm left with my copper and my cobalt. I can go add ammonia. I can go smell it. Hey, it smells like ammonia. I can centrifuge that, decant. So now I've separated my copper. Then here's my cobalt, and then I can go adjust my pH here to like pH 10, or go to pH 7, go back to 10, and I can go add, say, like carbonate, and go form a cobalt carbonate. So here's a way that I can do chemistry. So the idea here is not just to replace a real qual scheme that you might do for real. The idea is teaching students the chemistry while they're performing a game or a function and trying to discover what's in it. So I can click here and discard it. And then what I can do is I can create practice unknowns. So here I'm back in my stockroom, but now I'm doing randomization options. So I'm going to go to a minimum of 0 and say I want a maximum of 3. So this means that if I define cobalt, chromium, and copper as my unknown, okay, I can create and practice unknown, and it shows up over here. Bring this, and I know from the color that I don't have anything in it. Let's go discard that. Now let's go get a different random unknown. And I know I have at least chromium, so I can go through and do my separation scheme. So I'll go to NaOH, I'll centrifuge, I will decant, and I'm left with, could be cobalt and copper. I'll go add my ammonia, centrifuge that, decant. So I went from 0 to all of them. It's a random number generator. Then what the students do is they go to this lab book, they click on report, and then they report what they think it is as a practice and click submit, and they say, hey, I got it all right. So this is a way for them to practice their unknowns. Then what you can do is create real unknowns. So here's just where the clipboard comes in. So we have 3 different kinds of unknowns. We have these knowns and unknowns, or here's chloride, so that's known. So if they click that, it will create a test tube with those knowns in it, all right? or I can come to my clipboard and do a chloride unknown, and it shows up over here in my unknown rack. And you'll notice that the label says unknown number 3. So we can give you, the instructor manual would tell you what's in unknown number 3. They would go through and do it. Then they would report to you, I got assigned number 3, here's what I think it is, and then you would go through and grade it. So, you know, I can go add my acid, go add my sodium chloride, I can centrifuge, you know, I'm gonna go add my heat, centrifuge that again, decant, and so, hey, I don't have lead, right? I can take off my heat, go add ammonia, and I'm pretty sure here that I have silver. I can go add my amine. Yes, I have silver. That's what I would report. So another way of doing an unknown is these advanced unknowns right here. So advanced unknown, we have these predefined groups, and they're all geared around stepping students through different groups of cations, leading them all the way up to a full cation set. So that would be all 26 cations except for ferrous, all right? And so these get reported differently. So the way these get reported is, here's my unknown, but notice there's no unknown number. The way they get reported is you go back to the lab book and you have another report button, and you click on your buttons, and then this gives you a report. I got lucky, got them all right, and now they can report this. The way they would report this is they would come over here and save the file. So I'm going to come over here, save my file, save it, and now I've saved my file and all of my notes. You know, I can come back here and save it again, replace it, and then what you can do with this, if I exit, come back, there's that lab book file. What they would do is they would either email that to you or they would upload it to your LMS system. Most LMS systems would then append on here their name or their student ID. And then what you can do then is grade these. So these are not in a PDF or a Word or a Google Docs format. These are in a proprietary format because we have to save all of the experimental data in there to reproduce those links. So we can't do that in PDF. So then what you would do is you would click on lab book here and click on file, click on open, and then you would see a whole list of them right here, and you just double click on them, and then boom, you go look at this report and see and grade their answers. All right, questions, comments?
Can you show titrations, Brian?
All right.
And specifically how unknowns work in titrations as professors are trying to match up with a different, right, a software to match what they would have done in a real lab.
So in titrations, we have beakers, pipettes. So we have 5, 10, and 25 mil pipettes. We have a burette. We have a pH meter I can turn on. Here's a conductivity meter. So you notice that these are not calibrated yet. So we have buffer solutions to calibrate it. Here in the stock room, I can do titrations for oxidants and reductants. I can also do, and then we have acid base. So a student can titrate any of these acids with any of these bases, or any acid with any acid, or any base with any base. So like, what would happen if I added a strong base to a weak base, or a strong base to a weak triprotic base, tribasic base? And so we allow for, we calculate the pH of those solutions as you do the titration. We don't use Henderson-Hasselbalch. We do a complete charge balance, mass balance solution for up to a triprotic acid and a tribasic base. We include activity coefficients, partial molar volumes for the volume calculations. We use D by Huckel, extended D by Huckel to calculate the activity coefficient. So this is as accurate of a calculation as you're going to get. So, you know, a student could come over here, do a KHP, do an NaOH, and then this is just an example of, I was showing you of, hey, I got to go teach them how to set this up. So I got to go fill my burette. There's my window for my burette. There's my KHP. I'm going to have to go weigh it out. So I'm going to have to get my weigh paper. I should tear it. You know, I have to open my lid, and then, you know, so here's a little bit different scoop sizes that I can add. And so now I've weighed it, and boy, I forgot to go put my beaker. So bring my beaker back here and add that, and then add the water. I can, you know, keep on doing that. I have graduated cylinders, put it on the stir plate. Now I have to pick my indicator, and so on. I'm not going to go in the interest of time because I should show organic, but I can also come over here and I have these presets. So here is a strong acid, weak base preset, right? Here's bicarbonate. Here in the lab book, it tells you what the mass is. And then I've already weighed it out. It's 1.5 grams. Here's the HCl. And I've already selected an indicator, which is the methyl orange. The pH is 8, conductivity is that. Here's my graph, and now I can start doing those titrations. So that is, notice it says unknown number 2. So this is a way of getting unknowns. Again, we have a table of what those concentrations are. They can report the unknown number and then report the concentration, and you grade them manually. So I can save this data to the lab book. I can save this graph to the lab book. So I can change how fast I go. So I can do dropwise, you know, super fast, kind of fast drops. And so do all of that. And then I can stop, go to my lab book, and here's my pH graph. Here's my pH data. Here's my graph. Here's my data. You can copy, and then they can go analyze this. Or you can tell them, don't save the data, go use it by color changes of your indicator. Either way, that's one way of doing your unknowns. So those are on the clipboard here. And so you can see that we have strong acid, strong base, weak acid, strong base, strong acid, weak base, polyprotic acids, and then we have NaOH standardization and some redox titrations as well. An alternate, and this can be used as a practice titration or as an assigned titration, it's up to you, is you can click on that unknown sign. And so you notice I've selected acid base or use this lever to go pick. And then what I can do is I can pay, hey, this bottle, I want it to be an unknown base. So I want it to be sodium hydroxide, and I can define the min and the max random concentration. And then by returning to the stock room, I now have an unknown, okay? It's not numbered. Nobody knows what it is until they report it. And then they would have to pick the correct, oh, I'm gonna go pick my 100% pure KHP, and I'm gonna standardize that. And you can pick any of these reagents here to be these unknowns. And then when you're all done, you'd go to your lab book, you go to report, and then you would put in your 0.1123 and click submit. And then it shows you what the real answer is. And then they would do the same thing, submit that to you. Now, they can't go, next time they go get another unknown, it's going to be a different concentration. So it doesn't help them to cheat. And so this is just another way of doing unknowns. Numbered unknowns, if you wanted to get something more particular, a different concentration region, a particular chemical, then that's how you would do it. Questions?
I think I've answered many of them. Feel free to unmute if you have further questions. There were certainly more questions on how the lab books work, but I think you could also show that off pretty clearly in OChem.
Yeah.
So we've got OChem, biology, and physics that all want to be shown off next.
So I just want to show you calorimetry. We have coffee cups. We have bond calorimeters. You can do combustion calorimetry with organics. I think we have 80 different chemicals. Solution, You can measure the heat capacity of these 64 different metals. We even have sodium and cesium. So if they're clueless and they drop cesium into their calorimeter, it's going to blow up. We have heats of reaction. Again, here's clipboards. You can do Hess's law calculations. You can do heats of fusion, freezing point depression. So this is the calorimetry lab. You can advance your time. We also have a gases lab where they do various experiments exploring real and ideal gases. So I think we've covered general chemistry.
May I ask a question about access? Is so when the students buy in the access, Brian, by the way, thank you for your email. You sent me an email a couple of days ago. I inquired about a summer lab at Scripps College. So if they buy access for the Gen Chem, and I think you mentioned it's a 1-year access.
Yes.
And
they get access to all of them.
OChem, physics, all of them.
They get all of them.
Oh, yep. That's nice, because my students this summer were definitely online at Scripps College. It's a small private, the post-bac program. Come fall, there's no decision yet, right? Come fall, they will be taking OChem, and they could be doing online as well, so they don't have to pay again.
That's right. So we have all of these different products, and all of the worksheets come with a single license, good for a year.
Okay.
All right.
I just if I can do a cheap plug-in for you, I teach at a community college, and you probably heard that the California Community College has bought into Labster. It was provided to us from the hierarchy up for free. It's nothing.
Well, they also bought into us.
Oh, see, who? The entire community? We don't know, because if I know, then I would launch you.
So Peralta District, Los Angeles District, Rancho Santiago District at a minimum. Yosemite has contacted us, and Yosemite said that the California system was going to be trying to purchase it for everybody for the community colleges.
Oh, I got to contact because what happened with Labster, it was bought at the very way up high. I think we call it the Chancellor's Office of the California Community College. So all community college were given it, and we weren't even included in the conversation which one to buy in. But and I wish we would have been given this. I have this at Cal State University Channel Islands. I just want to mention that this is far more better than what we have with Labster.
Okay, well, that's good to know. I mean, we're in contact with them, so we're working with them. I don't know how long it will take, but let me get going on some of these other labs.
Labster, we're in contact with the school, with the community college districts.
I know Labster as well. I know them, and so I mean, Labster's fine. They just have a different approach than we do. We're all about open-endedness, and they're more about storylines, and they're on rails, and so it's just a different approach. All right, so here's organic. Let me kind of go through this really quickly. So same idea, lab benches, worksheets. We have about 120 of those organic worksheets. Here in the synthesis lab, like I said, these lab benches are all different. This is a procedural lab in the sense that you have to go through a series of steps. Here, what we have is a series of reactions, so aldol, Diels-Alder, epoxidation, and so on. And each one of these defines a set of starting materials. So just because I'll do an alkene hydration doesn't mean I have to do an alkene hydration reaction. This just defines different sets of starting materials. So if I do a esterification, these are my starting materials, and what I can do is add 0, 1, or 2 of these starting materials to my round bottom flask. So I can do any order, any combination. I can add a solvent. I don't have to add a solvent. Solvents adjust the reflux temperature if you're heating it up. And now I'm access to these 14 different reagents. So I can add any of these or none of them. So for esterification, I want to add, sulfuric acid. So I add some. I can heat, here's ice I could add, here's heat. So I'm gonna go add heat. I need to go add my condenser. If I don't go add so we have an outcome for all of these combinations. So what happens if they don't add the heat? Well, then it's it could take forever, right? It could take 5 hours. And so time is important. If you don't add nitrogen, this is going to blow up. So I show here what's in it, and then I can click here to start the reaction, and the reaction starts. So what's important here is, do I get the product? Did I pick the right starting materials? Did I pick the right reaction conditions? Now I can do TLC. I can drag a TLC plate and say, hey, I'm getting product. This is at least working. I don't know what I'm making, but at least I'm making it. I can save that to the lab book. And then I can advance my time. I'll go back 20 minutes and I'll do another TLC. Hey, I'm almost done. So the kinetics, these are all real kinetics based on published rate constants for the various temperatures at which we run these reactions. So heat, refluxing at this temperature, refluxing at a certain solvent, ice or room temperature. We'll have the correct kinetics that are going on. Let's go another 10 minutes and I'll do my TLC. Notice if I do TLC, my time advances as well. And now I'm done. So now I know that my reaction's done. So now the students, instead of just saying, hey, I'm just gonna go run it for 6 hours, they need to know how long to run it and specify that in their lab book, which is right here. So I'll click save, click OK. Here's my lab book. And there's the TLCs that I saved. And so they can take their notes. So now I need to work it up. So I'll take my SEP funnel. And there's my SEP funnel. There's my product mixture. Now I can do an extraction, pick the right aqueous reagent, drag that. And then we're going to add diethyl ether as part of the extraction. So I have an aqueous layer, I have an organic layer, and I can then take the organic layer or I can take the water layer. Doesn't matter. Like I can take this here, and then I just got my water layer and I just tossed my organic layer. So that was a mistake. I shouldn't have done that. So I just want to show you some other things we can do. So let's say they make a mistake and they add their starting materials and they say, okay, I'm going to advance my time, but I didn't add my reagent. So I didn't make anything, but they're oblivious. I can go add my subfunnel. I can go add my aqueous, but I could go do something like add my sodium hydroxide, and then I'm going to pull my acid into the aqueous layer and then pull this, and maybe they don't know what they've made. So now I pull my organic layer. Notice I pulled my ether off, and now I can go do my analysis. So they can confirm, hey, did I really make? So here's NMR. They can zoom in, look at the peaks. These are peak numbers. You go down to the peak numbers to see what the integrations are. You can save this to the lab book. These are all real spectra. So I can do a carbon-13. So let's say that you're teaching organic 1. Maybe you're not going to do the spectra yet. Maybe you just want them to go do a reaction to see, hey, well, it's a lot different than drawing a reaction on a piece of paper to actually go do it in the lab. Here's a mass spec we can do. Again, it's all real data. Here's FTIR that we've done. And so now they can confirm what they've done. So I'm rushing because we got other things to show, but that just kind of shows you how how that works. And then we have qual.
Hold on just a second. There was a question on percent yield, Brian, and how to control amounts.
So we're not quantitative in the sense that they can measure what the percent yield is, but I don't want to start it up again, but let's say that they stop it too soon, or maybe they don't get the product they want. The TLC size of the spots does give them a qualitative measure of how much of each is in there. So we are tracking amounts on a molar basis as we go, but we don't have any quantitative measurements to actually do percent yield.
And techniques, we've got distillation and we've got separatory funnel.
Yeah, and we've got recrystallization. So if you make a solid, You can recrystallize it to show what size of, what kind of crystals, what color do you make. So like the product may be white, but then you can recrystallize it to say, hey, it's actually yellow crystals. So here is the qual scheme. And so what this is are functional groups and a general unknown. So if I go to aldehydes, these structures you're seeing there are the actual knowns that they can practice with. So if I click aldehydes, these are knowns that they can go through and do analytical work on to go say, yeah, I'm comfortable doing I'm comfortable doing this work. And then they can go pick this unknown. So I just picked my unknown. It's always the bottle on the right. I take it out to my cork ring and it says unknown 210. So we have a table that shows what those are in the instructor manual, gives them the boiling point, percent carbon, percent hydrogen. Now they can start doing, again, their spectroscopic work, but you don't have to do that. Maybe you want to focus on these wet tests. So here's series of wet tests so I can go over here and we have these, I think there's 15 different wet tests and they can, so here's Jones, for example, and I can drop that in there and we're going to show you a real picture or a video of the results. So if time is important, then we're going to show you a video that gives important information. If it's a solid, you can do a melting point. And so these are available. So this is one way of doing an unknown. You just have them pick one of these or a general unknown. So here's your general unknown and, add this. And this is unknown 226, right? And so that's one way of doing it. The other way of doing it is on the clipboard. So we have about 300 unknowns, less than that. But we also have these random unknowns. So if I go do aldehyde, notice that it gives me an unknown, but it doesn't give me a number. So this unknown is random every time a student picks one. But notice like this is a solid. So for example, I could do a melting point on it and that mouse over here and it shows you what the melting point is. And I can do these wet chemical tests, but the way you report these, it's just like you did in the other one. You go to the lab book, go to report, type in their name, click submit, and then they save the lab book and upload that to the instructor to be graded. So that's how they can handle the unknowns. All right. So that's organic. Any questions about that?
I have a question for you. How many technique experiments do you have? You said you have recrystallization. What else?
You mean inside the organic lab?
Yeah.
So, so in terms of what we've written, in terms of our worksheets, most of the worksheets are targets to making specific compounds. You don't always have to make them do all the analysis work on what they do, but choosing the right starting materials, reaction conditions, and how long it takes, and writing out mechanisms, we have a lot of those. We also have techniques in terms of analyzing spectroscopy. We have worksheets in terms of using TLC. We have a worksheet in terms of doing lots of worksheets for qualitative analysis. I'm not sure that we have anything specific to distillation, but we just posted it up on YouTube, or we will today, I hope.
It's up.
A distillation example. And so you are certainly welcome to devise a way of doing a distillation technique. I don't know that we have a worksheet on distillation itself, but you can write your own one if you want. Okay.
Thank you.
All right. Biology. So we have biologists, or are we looking at the molecular biology?
It wasn't specific. Feel free to chime in what type of bio the bio person wanted.
Well,
actually, I was interested in the microscopes, and also actually I teach microbiology. So the part of making slides or things like that?
So we have, this is our microscopy lab, and we have TEM, SEMs, compound scopes, and dissecting scopes. So we don't really focus on making the slides.
Okay.
We were going to do that, and then we quickly discovered that there's an unlimited different ways of doing slides. And so what we do is we have a series of, we have a set of species in our lab here, about 175. And this is a, a species selector. Sorry. This is a species selector that lets you look at these different species with the correct scope. So for example, and then these are different ways of organizing and finding them. So if I go to P, I can go to paramecium. And so we have lots of cool images of these species using the correct scope. So this is what you would see for
Right.
paramecium. So here's a video. So here's one with the different kinds of staining. We also have on the same samples, the same ones that we purchased, SEM micrographs. So we took almost all of these species, all of these pictures. So we have 3,500 images in our microscope library that they can go and kind of look at, what do I see for these different kinds of scopes? All right, so that's kind of how microscopy works. Let me just run through this really quickly. Maybe take me 4 minutes. So here, what we have is genetic models. So I can go say fruit fly, and I can go pick traits. So eye shape, you know, or head shape, like leg-headed, for example. And we have all of the genetic models. So it's not just Mendelian. We have epistasis, we have gene linkages, we have incomplete dominance, sex-linked genes, you name it. We have all those different models, and they pick a trait. They can randomize, you know, the genotype for the parents, or do it randomly, and then they can do a cross. And then when they do a cross, you come down here and you see what the parents were, you see what the offspring were. And of course, I'm not getting anything over here because I had a homozygote parent, right? So I'll do this again and go back here to leg-headed and make it heterozygote. I'll do my cross, and now you can see your statistics, and you can do another one to see more statistics. And then what you can do is mouse over each of the individual ones to see what the traits look like. So it's not just here's on a platter some data do a Punnett square. They have to go kind of pick the right conditions and then analyze it and see, hey, is it really Mendelian? Is it not Mendelian? So we have all of these different genetic models built in. I'm not going to go through and show this one, but this is our molecular. So what we have is we've gone through in GenBank and created a mini genome for each of our species of 20 to 40 different genes, common genes between families. And you can take epinorth tubes and add DNA for different species, and then you can add the tag, and then you can go and pick primers, and then you can go and add this to your PCR, run a PCR, then you can go run a gel, and then you can go sequence this on your sequences. So we have, again, presets here. So here is a sequence for the, and the chromatograms that we've done for fruit fly and house flies that compare them. So you can do a molecular ecology, you can define biomes, you can put species into these biomes and let them interact and see the populations over time. And on this one, these are systematics lab, where you now take all this data and you can start putting them into different phylogenetic trees and take species and pick different approaches and try to see what species are related to each other. So sorry, that was really fast, but that's what biology gives you in terms of what you can do.
Hold on, let's unmute and just see, does anyone have a question they want to ask on biology?
Yeah, we were interested in dissections. I guess you don't have dissections needed.
No, I'm sorry.
No, it's like making no dissections. Okay.
Yeah,
Thank you.
we'd love to do that, but
Yeah,
go
can
ahead.
you take us through the systematics lab really quickly?
Mhm.
Okay.
Yeah, systematics.
So the idea on systematics, so here's the idea of what we did. So obviously I'm a physical chemist, I'm a low temperature physics guy, so I'm not a biologist. So I had two collaborators, Keith Crandall at George Washington and Riley Nelson here at BYU, that we put this together. The focus was modern biology and focusing on diversity. So how do we look at diversity in terms of their outward appearances, microscopy? How do we do it in terms of genetics on a DNA level, on the ecological level? And so the whole idea was to take all that information, and this lab would be the way to kind of assimilate it all together. So the idea is to say, hey, take a species like fruit fly. Where does it sit on a tree? So we have different trees we can use. We have a 3-domain, a 6-kingdom. We have a Linnaean. You know, we have a simple makeup one that we did to kind of demonstrate how it works, and we have the true tree of life, the current phylogenetic tree from the book Tree of Life. And so we have different schemes that we can do. And so what you do is you can pick here, a student can pick and say, okay, what is you care? What are the traits for that? So they'll mouse over it and it comes over here that these are the traits you're looking for. It has cytoplasm, multiple multicellular nucleus. And so you can click on nucleus and see a glossary and see a definition of what each of these different terms are. So we have all of these definitions. And so they look at this guy and then they say, oh, well, it's multicellular, so it's probably eukaryote. And so you see the species that don't belong in that category. And then you start going through and you say, okay, it's probably Animalia. And then you start seeing ones that start getting kicked off into what we call our discard pile. This is our keep pile. And then you start looking through and defining, all of these different, and I don't even know because I'm not a biologist, and then and they try to organize it, and then you can zoom out and then you start looking at how species are related and what their traits so that you can really organize the species. So that's how it works. So it's actually pretty cool.
And you can change which trees you were going through.
Yeah.
Did you? Okay, sorry.
Yeah, different. So we tried to match different books. So we definitely matched the one that's in Campbell, because this used to be a Pearson product. So we actually have Campbell's tree in there, but we also have the real one. We also have some other more simplified versions. What?
The real one. A lot of people say theirs are the real tree. But yeah.
I know. Okay. All right. Go talk to Keith over at George Washington. Yes, he's a evolutionary biologist. So I had to go through all of that stuff and actually learn it. All right, let's end up with physics really quick. So same idea. So in physics, what we do is we pulled in the benches from general chemistry, quantum, calorimetry, gases, but we added these 4. Same idea, worksheets. So this lab is probably the lab that will be used really heavily, at least in the first semester sequence. When we're doing mechanics, is what we have here is a 2-dimensional experimental table, and then you can go in here to the stock room and you can pick solar systems and planets, and you can pick ramps, objects, forces, frictions, and gravities, and play around with them on this table. So I could pick, for example, my downward gravity. I could go pick a rocket. I could pick a ball, and I could go pick my air friction, and I can click on my table, and now I'm on my 2D table. I can go put my ball out here. I have parameters, so I can go and change diameter, mass, all of these different kinds of things. I can collect the data. I can record data, change my units, change my timescales. So I can click start and nothing happens because there's no force. I had the idea for this lab when I taught physics at a small school back in 95, 96 in Virginia. And I was trying to do experiments and the kids always got confused about gravity because it's always there. So I can reset and then show them, hey, if you don't have any gravity, nothing happens. So here's gravity. Then I can click start and then it falls, you know, and then here's this data showing what it is. You can record it, have them graph it. Then I can reset my experiment and say, hey, what happens if I add air friction? So now I can click start and start seeing that my acceleration is changing. So I can change my mass, my diameter, I can come down here to frictions and change the barometric pressure to see how that affects things. And then I can come over here and say, hey, I'm gonna go put on a rocket and I'm gonna go launch this rocket. And so we'll have that motion for that. So we can do lots of these different things. Billiards, so we have collisions, momentum transfer. Here's my plunger launching this. We have rotating friction, change the elasticity. You know, we can do like radial gravity sink and launch my rocket.
Can you show the type of data that's saved for these, Brian? So
sure. So
so
for example, you can tell them which ones to save, and then I can click on my record button and then click force and then record that data. And then if I then click stop, I can click pause here and it stops the data, go open the lab book. And then here is all of that data. So you notice that I was in a polar coordinate system. And so I saved the data, time, R and theta. And so all that data gets saved here and they can copy it, analyze it in any way you want them to go do that. So solar systems, stuff you could do. We have a density lab. Optics lab is pretty cool. Well, they're all cool. So here you can take a virtual eye and take an object and see what that object looks like. And then you can throw in mirrors, for example, right here. And then I can rotate my mirror around and see a sight line. Now I can go see both of them. I can change on my gear here. It's the flat mirror. I can change its curvature. I have lenses, prisms, different objects, lasers. So you can teach them about, you know, a concave mirror at the focal point or a concave mirror between the center, the focal center and stuff, and see what you're going to get. So you can change what colors. You can do colorblind. Hey, what is a colorblind person going to see? So we have that for objects and circuits. So we can have them build up to 35 components. Any type of circuit with resistors, inductors, capacitors, light bulbs. We have function generators, batteries, multimeters, and an oscilloscope. And you can build it on the breadboard, or you can build it on the schematic, on the engineering paper. So if you build it on the engineering paper, you see it on the breadboard. If you build it on the breadboard, you see it on the engineering paper. So you can do these different types of experiments. So here's a discharging capacitor, for example. And so that's what we have. So that's physics. Lots of cool things. You know, all of these labs, you know, the circuit lab, we did a generalized solution using Laplace transform to transform it into Laplace space and do the solutions in the Laplace space and then transform it back to real space. Optics are, you know, your lens equations. Mechanics, we developed our own Runge-Kutta adaptive 45 algorithm to do all those solutions in real time. So to involve all of the forces and frictions and all of that. So that's a very fast overview of them all. Physical science, it's just physics plus chemistry together. It's kind of geared towards a middle school, high school experience. But there's some great density labs. Like I said, we're finding some teachers are using density experiments to talk about solutions and miscibility, things that we didn't even think about. So lots of things you can do. All right, questions?
Question on pricing. There was a quick question on how we do licensing as a whole. I answered that one. Could you explain our pricing levels?
Yeah, so generally it's $25 per student for a 1-year access. If a student buys it from our website, it's $25. We generally start looking at discounts when we start getting to the 300 licenses for institutional purpose. So we start doing discounts at 300. When you start getting up into the thousands, to the 1,000, then we start doing way more. And so, I mean, like we're talking a 20% discount when we get to like 300, and like a 40% discount, or don't quote me, I haven't done the math in my head, but it starts getting more as you get up into really big, larger numbers like that. So we definitely have those kinds of discounts. I recognize that big is a relative term. For some schools, 25 is big. For some schools, 500 is big. So, I mean, I happen to teach 250 students, so to me, 250 is big. Does that answer that? So faculty access is free. We throw in extra codes for faculty and TAs so they can do grading or use it or play with it.
Brian, you had mentioned you might quickly show off the HTML5 version that we have.
Sure. So we know that we need to go into HTML5, but I think you've seen that that's a heavy lift to do that. These are not trivial, one variable simulations. There's lots of graphics. Each one of those labs may have taken 6 months to a year with 24 undergraduate students doing the artwork just for that. So porting this over is a heavy lift, but we're starting. We have some prototypes. Hopefully in May, at some point, we're going to have some very basic access to 3 labs that we've got ready to kind of play with. So this is our acid-base lab. So in the acid-base lab, it's the same engines. This is limited. It doesn't do any solids. These are only solutions. But you can see that this product is geared towards phones and tablets. Obviously, it works on a computer, but that's kind of with the direction we were going. Our staging is going to be, we're going to take our current labs with the current graphics and move those into HTML5 and then start working on these. But last year we started prototyping all of this kind of work, so we knew the cost structure. But here you can see how this would work on a phone, that you would have a experimental view here, and then you would have this tray that slides out where they can go take a beaker and drag it down. And then we have this other side over here, which would be the details and the cards. We call them the cards. And so I can take like acetic acid and drop it, and then I can fill it up some amount. Then I can come over here, open my tray, go to pipette, and click on the pipette and suck up 25 mils. I can move this back here if I want, or I can put it in the trash can. Get another beaker, click, and now I've got 25 mils. I can put it on my stir plate. I can start stirring. I can add an indicator, so thymal blue. Here's their indicator, so you can see the colors, you can see the volume. I can come over here and get pH meter, add that. So now I know what the pH is. Get my burette, add that. Come over here, get a sodium hydroxide if I want. And fill that up, and now I can do a titration. right? So I can click here and then control the rate. And then I scroll down here, here's my graph, what's going on. I can see what the pH is at different points. There's a way of viewing the data. So this will be like one of our first ones to come out, titrations. This one's pretty much done, got a few little bugs in it. What we're working on now is the wrapper around it. Notice here that we have eight all of these different indicators. We have these different acids and bases, water, and a series of unknowns that can be given out. So this, you're going to see it's ugly. We're kind of converting over to our color schemes and stuff, but here's our inorganic lab right here. So we have a single test tube. We can click here, and so here's my cobalt, chromium. I can add my copper, and then we instead of a real picture, we couldn't do with these real pictures, and so we're doing. We took all those real pictures and created these graphics for them, and then I can come over here to my bottles and say I'm going to go add sodium hydroxide. I'm going to come over here and centrifuge it, and then I can decant, and so we can come over here and kind of do the same things. We got a little bug here for our icons aren't showing up. So here is, I can go add, where's my ammonia? There it is, go add my ammonia. Come over here, centrifuge. So here, this is the inorganic one, same idea. Same labeling, you can make copies, you can throw things away, you can heat it. It's just, it's designed for tap. So this is the direction that we're going. So we also developed, while we're at it, we also developed a anion lab as well. That's not in the current one. So hopefully that's going to come out soon. All right, we're working on it. Bandwidth is our problem. More questions?
You know what? I have used your text, your lab manual, virtual lab manual. Probably it was 2010 or 2011. It was from Pearson.
Right.
And how I knew that, and I went into Google and it said it's out of print. So, but luckily I got through to you.
Yeah, so we've updated all of that content. We've updated the labs, but essentially, you know, we haven't changed the underlying engines and underlying simulation. So they're the same. The content's now available on those PDFs, so we don't have to deal with printing and delivering those workbooks.
So
But you know, if you guys felt like the physical workbook would be useful, we could probably take our PDFs and make one at some point, just not the next 3 weeks.
So not right now, because we are all doing virtual labs. So, you know, not right now, but maybe in future. And the other thing is, I wanted to tell you something. I forgot. I'll come back to you again.
Anybody else while she's remembering? I have that problem all the time.
Brian, very nice. But I have a question. Sometimes students don't have computer or they break down. They can do this thing on their mobile devices?
Now, this is Mac and Windows only right now. Now, what we would, you know, obviously the size of schools is highly variable. Some schools have taken our Windows version of it and either hosted it themselves or paid a service to do it, where they host it on an app server. Typical examples are Citrix, Aporto, VMware. Apache has a free one, but it's a real pain to set up. And so they will get an app server set up so that students with tablets or Chromebooks would then access the app through their browser and manipulate it through their browser. I've been told that it's an acceptable experience. We're not experts on how to do that. All I know is that it's possible. My two youngest children, my two youngest are in college, and they have used that type of service to get access to their stat packages, which are, for example, Windows only, and they're on Macs. And so that's how they get to stat packages, for example. So I know it's possible. We're just not the experts on it.
All right, thank you.
My question was, a student pays $25, supposing we need it for organic too. And you know, all your synthesis and you know, your NMR spectroscopy, all those things we need it. So the student pays $25, he or she will have access to general chemistry as well as the entire chemistry, or just one organic chemistry?
They get access to everything. So when they, so let me go share my screen again. So when they, get Beyond Labs, this is what you get, is you get this client, and they can install all of these products.
Okay.
And they get access to all of the worksheets.
Okay. Thank you.
Yep.
And what about the teachers, the faculty? How much do we pay?
So when you purchase, like, so if you have your students purchase it directly for $25, then you just say, hey, I'm having my students purchase it, and we'll give you a code for however many faculty are going to be using it and TAs, and we'll just give you a free code for that.
Yeah.
If you purchase like the group of licenses for your students, like it's coming out of your lab budget or whatever, then we would just throw in an extra, depending what size you are, 2, 3, 5, 10, whatever you need, extra licenses for you guys to do it and install it for free. So faculty are free, students pay, just like textbooks.
Okay. Thank you.
Hi, I have a question. For biology, there's some labs we do like enzyme reactions and photosynthesis. Are there experiments like that for biology?
No, I'm afraid not.
Okay.
That's on our to-do list, is to do that.
Okay. Thanks.
Yep. Anything else? Now's the time to ask.
All right, one
Pastor.
more question.
Uh-huh.
Brian, for example, if there can be a variation in the data among the students whenever we are doing any experiment in organic chemistry, because usually in the real lab, we always have variation. You know, students are getting different yield, which you told probably we cannot control that. Even some impurities or whatsoever. So there will be any variation, or they will be all getting same results because they end up into writing the lab reports. There is no variation. They may be copying each other, and that will be.
So for organic was geared around being a qualitative approach. I mean, so I'm a practicing scientist, right? I mean, I want students in a real lab as well. And so we never designed these labs to be strictly lab replacement. Like I wasn't going into a school and saying, hey, you can do better with a virtual lab and you don't have to do real labs. Now, the administrators want that, of course, but I don't want that. And so we really designed these labs to be an augmentation for the real lab, as a pre-lab to get them ready for doing an experiment, as a post-lab to extend something they did, to give them practice for the lab exams or to do something in class. So for the organic lab, yeah, it's going to be highly reproducible. Probably the time element is going to be what's different enough. However, on our research, we published a couple of papers in JChem Ed back in 2005 and 6 or 6 and 7, I can't remember. There is a high amount of variability in the sense that students make a lot of mistakes, even though they think that they're following the directions. Now, I said that for organic. Now let's go back to general chemistry. In general chemistry, where it is quantitative.
we do have like the unknowns built in there that allow students to be generating something in OChem and
Yeah.
have variability that way.
So, but going to general chemistry, that is quantitative, except obviously the inorganic. But again, inorganic, we give them different unknowns. But for titrations, gases, calorimetry, and quantum mechanics, we build in variability that isn't the same. So for example, that balance has an error, and we're going to build that error. That volumetric glassware has an error. So when a student delivers 10 mils, it's not going to be exactly 10 mils. We build in volumetric glassware error, so that it's not real. There's buoyancy corrections in the mass. And so those errors are built in, and they are going to see the same variability that they would see in a real lab.
Okay, for example, as you said, if we can give the different time, assign different time for the reaction to different student, then the results will be different.
Well, what I mean by different time is you know, one way of making sure that the students just do it carefully is to say, how long does it take them? How long does it take to get to the product? And what you'll see is you'll see variability in the students, because some of them will do it like 1 minute increments because they're really detail oriented, and some of them are going to say, I just want to get this done, and I'm going to go 2 hours and say, oh, I got it, and it's 2 hours long. So you'll see variability that way, and you'll measure how careful they were in the experiments by how long it took, by how long they measured it took to get to the final product. And the other, so it's actually a really great question. I like the question. Okay, the other way that you deal with variability, say on the organic lab, is you don't give them all the procedures. So obviously the first time you give them a reaction and you say, here's the procedures, here's how you learn the interface, here's how you do the workup, and blah, blah, blah. But then what you do is in the next one is you say, hey, let's go do a Grignard reaction, and you know, here's your target, make it. So what you'll see is you'll see the variability from the students and how they do it, in the sense that maybe some of them use ice, or some of them use room temperature, or some of them use, you know, they reflux with heat, and then you'll see them in how they analyze their data to confirm what they've made. So it's in how you structure how they do the work that where you also see students. So we have great research on how different students handle the amount of structure you add to those assignments. Really fascinating stuff.
All right. Thank you.
So this happened, so I got to continue this because I'm on my soapbox, is we first piloted this in a high school back in 2000 in an AP class for the inorganic qual. And we had an A student, and a B student, and the teacher said, watch these two students. This one student's my smartest, it has the highest grade, but this other student is my smartest, but really doesn't care, right? And the A student got so frustrated because we wouldn't give that student, I'm being gender neutral here, wouldn't give this student the procedures, that this student actually took the keyboard and threw it on the ground and stepped on it out of frustration. Whereas this other student actually got said, oh wow, I can actually get into this thing, and really started asking for more experiments to do just because they could get into it. So controlling the structure is really key to the type of learning you're going to get out of using these labs. Any other questions? I probably talked over somebody, I'm sorry. We appreciate your time. We appreciate your interest in our product, and we'd be glad to help you out, and hope your students find engagement in using the labs and actually discover that science is actually fun and cool and not laborious and repetitive. All right. So thanks a lot for attending. We'll have this posted hopefully in a few days, and you can come back and visit and revisit things that may have been there. All right. I'm going to sign off.
Thank you.
I can't read your faces. Thank you.